In this video, you'll learn how to draw force diagrams. The first step that we're going to do to draw a force diagram is to indicate our system. And we can do that by drawing a system boundary, which is just a dotted line around the object of interest. The next step is to draw a dot. And then you're going to draw all the forces that are acting on this object. And we're going to start with the tail. For this lamp right here, there is going to be gravitational force. Now for all objects we'll see in this video, they're all going to be on Earth. And so anything on Earth will have a force of gravity acting on the object. Now there's a cable holding onto this lamp, so that is going to be a tension force. And a tension force is any time you have a wire, a rope, a cable, that will be called a tension force. And notice that the lamp is not moving up or down, it's not speeding up, accelerating, and so the two forces, these two forces are going to be equal in magnitude, equal length. Okay. Next, we have this little toy right here, spring toy, pop-up toy. And once again, I like to always start with gravitational force because all the objects we deal with will have force of gravity acting on it. Now you notice there's a spring, and we'll call that FSP for spring force, sometimes also known as an elastic force. And these are the two forces acting on this little pop-up toy. Next, we're going to take a look at this skydiver, parachuter, and he is going to be our, actually, I'm going to make this whole thing, let's go ahead and make this whole thing our system right here, so including the parachute, make the whole thing okay, our system. And then we're going to once again start with gravitational force. Okay. And since this guy is falling through the air, and that air has a significant effect on the motion of this parachuter, we're going to include air drag. And so I'm going to write F air right here, so this is air drag. Now let's say that this guy is falling at terminal velocity. Terminal velocity means that the person is no longer speeding up. Okay, it doesn't mean that the velocity stopped. That's a common misconception. It's not that the person's not speeding up, and it's not that the person isn't moving. So let me clarify that. Terminal velocity isn't saying the person isn't moving. Person is moving. What's terminal, what's not continuing is the acceleration. So at terminal velocity, the acceleration is 0, and the person's falling at constant speed, constant velocity, and the forces are going to be balanced. Next, we have a Rubik's Cube. This is our system right here sitting on a table. And we have our gravitational force. And then the table is a surface. When a surface is pushing on an object, that is called the normal force. And that's Fn. Okay, and now we have a box that's on a surface. It's pulled to the right at a constant speed. So we will once again start with Fg, gravitational force. The table exerts a normal force. These two will be balanced because this object is not accelerating up or down. And then this box is pulled to the right, constant speed. So there's a rope there. So we're going to call that Ft. Now, because it's going at constant speed, I know that this box is in equilibrium, which means that the forces are balanced. The net force is 0. So something needs to balance this Ft, and that's going to be from kinetic friction. There's two types of friction. If it's moving, we call that kinetic friction. If it's not moving, then we call that static friction. In this situation, it is moving, so that's called kinetic friction. Next, we have a box that's moving to the right and slowing down. So once again, we'll start with gravitational force. We have normal force, and those two forces are balanced. Slowing down, there's no more rope to the right anymore, but it's slowing down, so I know there's got to be some friction. Since it's moving, we're going to call that kinetic friction. Alright, let's take a look at some more problems here. Here we have an elevator. It's moving up at constant speed upward. We're going to assume it's not touching the elevator shaft. It's just moving up, and there's a cable that's pulling it up. So we're going to once again start with Fg. Okay, and it's moving at constant speed. So constant speed tells us, we know there's a cable force, okay, but constant speed tells us that this object is once again in equilibrium, when objects are in equilibrium, the net force, here's the symbol for net force, is equal to 0. Right? So that means forces have to be balanced. So I know I'm going to draw the tension force here to be the same length. So these two are going to be the same length, tension force and gravity force. Now this one, the elevator is moving up and speeding up. Okay, so the elevator's force of gravity, also known as weight, is going to be the same as before. It doesn't change. But now it's speeding up, so I know forces are unbalanced and the tension force is going to be greater in the up direction. All right, now let's take a look at this car. This car is slowing down. We're going to start with gravitational force and normal force. It's balanced because it's not accelerating up or down. It's slowing down. The brakes are, brake pedal is pushed, and so we are going to have friction, and we'll call this kinetic friction. That's going to be to the left. There is such thing as rolling friction, but for right now, I'm just going to keep it simple. We're going to stick with just kinetic friction to the left. Okay. Now this ball's all the way at the top, and so this is maybe a basketball, or it could be a tennis ball that you throw, projectile motion, and at the very highest point, there's going to be gravitational force on it, because there's gravitational force on all objects on Earth. And the highest point, let's say that we want to take air resistance into account, then air resistance is going to be the opposite direction that it's moving. So opposite direction. So it's moving to the right, okay? So it's moving to the right. We'll put a V there. It's moving to the right at this point. So the air resistance is going to be to the left. So the air resistance is in the opposite direction that the object is moving.